Welcome back to Simulation and Prototyping. Today I want to use the Orient tool, or the Orient component in Grasshopper, to map an object to a surface. And we're going to use this, we're going to do this in a couple of different ways, and I'm also going to add an attractor point. And so if we look on the screen, we can see an example of a surface, and we can see some of the other examples in the background. We can see a surface with an object that's been mapped to its surface, and then what I'm also doing is using an attractor point to rotate each object individually. And so I want to build this up with you so you can get an understanding of how I structured the geometry in order to get this to work and for it to make sense. So here we can see a couple of things that we can do in terms of mapping that surface. We can change in the grasshopper portion. We can change the point. And so we can see all of these panels slowly rotating. And what I'm doing is I'm using the MD slider as a way to change one point and then have all of these rotate. There's not much happening in terms of parametric control other than the surface and the object that we're mapping to that. And here we can also see the object that's being mapped is just a simple cube with two sides cut out of it. And the example that I'm using is this example, which is an older project by Monica Ponce de Leon and Nader Tarani. And we can see Casa La Roca. And it's this surface, or this basic idea of these cubes that begin to rotate. And so I can talk a little bit about how that geometry is working. It's a really nice project. It's worth checking out. We get a couple of glimpses of this wall. This is a different brick wall in the project, but if I continue to scroll, we can see this wall, this perforated screen wall over here on the left, and then I think there's another image of it here on the left. And so this is a nice precedent to use because it will use a surface and it will use that object. We can talk about orient and how we set that up, and then how we need to break it down and understand the geometry. So with that, and even what's kind of interesting is that the amount of things that are happening within the surface, the flatter, simpler surface might actually be a little more expressive to be able to understand some of these things. But let me start a new file, and we'll build this step by step. And it's should be a relatively simple thing to do once we have the geometry set. So I'll save this and this, and then why don't we start new? I'm going to work in inches, and I'll make a new. I'll just close this file. Okay, so I'll pull in the binoculars or bifocals so that we can see both the icons and the names of what we're going to work with. And the first thing that I'd like to do is to build our simple object that we're going to replicate. And in this case, I'm going to do this in Rhino and build a rectangle with 3 points. I'm going to do it in the front view. I'll start at 0. I'm going to make this 8 inches wide and 8 inches high. And I can also offset this 1 inch all the way around. And then if I select both of these, I can solid extrude planar curve straight, and I'll extrude it 8 inches. I can delete the curves, and now I just have that simple volume. I can expand this, and we'll use a control point curve, and maybe we'll make just a straight. I'm holding down shift, and maybe I'll do this with 4 points. I want to start and do it with a straight line, and we'll loft between 2 of these. So let's look at this in the front view, and we can copy that simple control point curve up. Don't need a lot, or we don't need a lot of height here. And let's just loft these together. Nothing special with the loft either. This will allow us to come back. Oh, you know what? Actually, let's make that parametric. So let's keep our 2 curves there, and let's start with that. So in Grasshopper, let's get a curve container and copy it, and we'll set these up as bottom and top. So the bottom curve, we'll set 1 curve and select that, and then right click, select 1 curve, and we'll pick the upper curve. Now we have these, and let's do the loft in Grasshopper. Add the first curve, hold down shift, and add the second curve. So now we have this. What's nice is that we can manipulate that, and it'll stay parametric. I'm going to undo that. I want to start with just a very simple flat surface so that we can see exactly how this is working. Okay, so we've got our 2 curves. We have our lofted surface. Let's also make a B-rep container, and we'll select the small solid that we made, and now we have that as well. Okay, so the first thing that I'd like to do is to contour the surface, and we're going to do that based on the height of our block. And so let's do the contour, and this is create a set of B-reps or mesh contours. Our shape is going to be our loft. The point defaults to the origin, and that's okay for us. The direction defaults to Z, and that's also perfect for us. The distance in this case is going to be 8 inches. And we could do something more complex. If we were to parametrically be changing our block, we could set it to the height of whatever that block is, so that if it changed, the contours could change. But in this case, and to keep this simple, I'm just going to create a panel because I know that it's 8 inches, and I'll add that to distance. So now we can see we get a series of contours vertically through our lofted surface. I'm just using Control Q to hide things, and I can even, well, I'll leave our rhino curves there so that we can manipulate them. So now what I would like to do is, because I want the bricks to stagger, I want to separate out the odd and even contour lines. And so this will allow me to work on them independently in 2 groups. And to use that, or to do this, I'm going to use the dispatch tool. Our list is going to be our contours. And let's see, the dispatch pattern we can see is true, false. And let's add a curve container to each of these outputs. And we'll see if it's working the way that we want it to. Not yet. So our dispatch pattern, let's do It's true, false. I want to set this to be, oh, let's see. If I hide that, so there's no values there and no values there. We'll hide our contours. And so right now everything is coming out of this. I'm going to use a panel, and I'm going to set this to be a multi-line data. Let's see if this works. Let's set 1 and then enter and 0. That seems to be working. Here's what I need to do. The problem is that I didn't flatten the contour lines. So now we can see as we select list A, that's this row, this set of every other curve, and then list B is the other set of curves. It's basically 0, 1, 2, and so it's even and then odd. And this is a simple way to set some of our Boolean patterns, a 1 or a 0, and I like to do that with a list. It's easy enough to include those. So now we have two sets of curves, even and odd, and let's look at a couple of different things. We're going to take each of those sets of curves and we're going to divide them. And typically we divide based on a number, but there's a really good tool called divide length. And so as we set this, actually that's not the one that I want. Let's find it. It's probably under curve, division, and divide length. And so divide length, we want to be specific as we set a series of points along that curve. And so our curve will be, let's start with the bottom row. And our length in this case is going to be the hypotenuse of our object. And so if we dimension our object, which we can do because we have a nice simple Rhino cube here, we can see that that's 8 by 8. And if I do an aligned dimension, diagonally corner to corner, that's 11.31. And so this is what I want to use for my divide length. And so let's come back down here, and I'm just going to make a very simple panel with 11.31. And we could even name this box hypotenuse. And so now as we set this dimension to that length, we can see a series of points added along the length of those curves. And again, it's every other curve. Let's do this for the second set of curves. But what I want to do is I want to do a half step with that. So I'll copy this. And rather than doing 11.31, let's do half of 11.31. So let's multiply this. So we'll use the multiplication tool. We'll set that to A, and we can just make a very simple panel, which is just / 0.5. So this will allow us to find half of the hypotenuse and set this to the length, and then we'll add that curve to it. And so you can see now we're getting twice as many points on the second row, but I can cull that pattern and we'll select them out from there. And so let's set this to be, we'll use cull pattern. And so we'll pull in these points, and our pattern will do the same thing. We'll use a panel, and we'll set this to be, I want to say, a multi-line data panel, and we'll set it to be 0, and then enter, and then 1. And now we can see that as we hide the divide by length, now we have a series of points that are alternating along there. So that's working well. Let's just get these kind of lined up here. So now we have our two lists for our series of points there. And the next thing that we're going to need to do is to set a plane at each one of these where that plane will also map to our box. And this way we can locate our object using the orient tool along those points. So to do that, I'm going to use I'm going to make a plane, although we're not quite ready to make a plane yet, but that's under vector and plane, and we're going to make a line plane. So we basically need two lines in order to set a plane to that location. And to do that, I'm going to use these points and make a line from each of those points using the line SDL, which is start, direction, and length. So the first line will start at the point. The direction will be Z, unit Z. And the length is arbitrary, it doesn't matter, but I'm going to make this 4 inches. And we can reuse this value when we do this for the other row as well. So now we can see, if I zoom in, we get a vertical line at each of these points. So now we also want a horizontal line. And the way that we're going to do that is we're going to pull the tangents from these. And so if let's see, let's do the same thing. And we can copy this. And we'll reuse the length. Again, the length can be anything you want. But this time, rather than using the Z value, I'm going to use the tangents. And as we draw that, we can see that the tangent line is there as it relates to that surface. So now having these two lines, we should be able to do that. And now we have a series of planes at each of those points along that surface. When I did this previously, the line went in the other direction. And so we'll see if we have to come back and flip the direction or not. For now, let's leave it as the way that it is. We have one minor thing that we have to change with our other set of panels. And let's start with just copying all of this. We'll move it down. And we'll change a few of these things. So rather than using our points, we'll use this list as the start for each of those. The Z stays the same, and the 4 stays the same. We can tie back and use that 4 or not. Doesn't matter for what we're doing. The one thing that we have to change is the direction of our tangents related to our points, because right now it's pulling the tangents from above. And you'll see that the output from here are the tangents. And I made a mistake when I did this earlier. I pulled these tangents from back here. But remember, we culled the list. So I'm going to duplicate that culled list. And rather than bring the points to it, I'm going to bring the tangents to it. It's still going to be the same pattern. And in this case, I'll use this culled list for the direction. And so now this is the alternating row of those points. So hopefully that makes sense. There's limitations in terms of how you define planes. And in this case, because we had that point, because the divide function comes with the tangents, it's easy for us to get those two lines as a way to then define the plane. So now that we have the plane, let's map our boxes to that. And so we're going to do this with the orient tool. And this is under translations, Euclidean, and then orient. And so what do we need when we orient a box, or when we orient an object? First, we need the geometry. So our geometry is going to come from our B-rep. I'm going to break my rule a little bit. Well, maybe I'll leave that at the bottom. I like the inputs to be over to the left. So what I'll do is maybe just pull this down. And we'll see a long line from that B-rep from the box over to the input for the geometry on orient. And our source, let's set a source value for our object. And that's going to be simply the XZ plane. Since it's already at the origin, we can just add that even here. So or we can find that under vector, plane, and then the XZ plane. So that'll be our source. And we can see as we click on this, it highlights the front face of our box here. We'll plug that into source. See that flipped that slightly. We'll see what happens. But let's do our target will be our planes here. So that looks pretty good for the first row. Let's grab the second set of planes. We'll hold down Shift and add this to the target here. That actually looks pretty good. I'm going to hide my planes. Again, I'm using Control Q to hide. We can hide our points and our culled list as well. Our curves are there, and those are hidden. So we have our simple wall. The last thing that I'd like to do is to put a point on our surface and use that point as a reference point to then begin to rotate each of these boxes in its own space. So the way that we do that is we're going to start off by making an attractor point. So for the time being, let's hide our boxes. And I'm going to use a really simple method to create a point on a surface. And we'll do that using the MD slider, which looks like this. And we're going to use under surface analysis, we're going to evaluate a surface. And so this is going to require two inputs for us. One, a surface, and that's going to be our lofted surface that we're going to evaluate. And then our point is going to come from the MD slider. As we move this around, what's happening is that if you zoom in, we are on the surface, but it's changing a small amount. And the reason for that is that as it comes to this component, we right click on surface and we're going to reparameterize this, because currently, before we reparameterize it, it's taking these as absolute values. Instead, what we want is to treat this as, let's see, we want to go from 0 to 1 in the X domain and 0 to 1 in the Y domain. So basically 0% to 100% across the surface. So once we reparameterize this surface, now if I zoom out, we'll see anywhere along this surface, we can locate a point. And so let's create a point container, which just makes it easy to capture that. We can hide the surface evaluation, and now we have this point in space. So we're going to use this in conjunction with we're basically going to understand this point in relationship to the center point of all of the previous boxes. Not the points along the curve, but the center of those volumes. So if we turn these back on for a second, we have those. The easiest way to do this is to use the volume tool. And if we double click and type volume, we're not really going to find the volume, but we are going to find the centroid. And so, same thing, we could create a point container, taking the centroid from each of those. So as we zoom in, we can see there's a green point at the center of each box. So we can hide our volume. Even let's hide our boxes there. So now we have the points that are tied to the location of the boxes, and we have our green point here as our attractor point. What I want to do is remap the distance from each of these points to this focus point, and then add a rotation based on that length. So the first thing that we'll do is, let's pull this point over. We have these 2 points. Let's create a line so that we can visually see what this is. And we're just going to do a line between 2 points. Let's do our start point as the points that come from our object, and the end point being our focused point there. So now we can see each of these lines will have a length. And basically what this is telling us is that from our attractor point, wherever that is, each of our boxes will know how far away it is from that focus point. I'm trying to find like 1/3 in terms of its height and 1/3 in terms of its width. So now, having each of those lines, we can find their length. So we'll use the length component, the curve length component. We can plug this in. And what I want to do is to let's see, take each of those and basically remap them. And so remap is a very useful tool. And what it does is we take our value, and the value will be our lengths. We're going to take our, we're going to map it to a rotation, and we're going to look at the source. So let's understand this a little bit first. Well, we know we can plug in our lengths into the values. That's fine. But let's understand what those lengths are. So I'm going to create a panel. And we can see each row. We can see this is ranging low. I see 22. Yours may be different. 13.7 is a low number. And so an easy way to do this is to understand. Let's take our domain. Let's see, is it bounds? So if we take all of our lengths and even flatten this down, our domain, so now we can see that our domain, basically the min to the max, is 6.7 is the smallest length, and the largest length is 117. And so we can map that source directly, but we can also set that to be something else. So let's, maybe if we make a panel, it's easy then for us to understand what these are. And let's set our source to be, well, for now, let's set it to be exactly that. What I want to do is come back in a second and crop that a little bit, but we'll see the difference that it makes. And for the target, let's give it a simple domain. We can do this with a panel, and let's say 0 to 90. And so what's happening as we remap these is that every dimension that comes in is the value. The source is telling us its min and its max, and then we're remapping that to 0 to 90. Let's use that then to rotate the boxes. And so we'll do this with a simple rotation. And what do we need? We need our geometry. So we're going to come back and grab our oriented boxes, which are here. We'll take the geometry that comes out and plug it into the geometry there. For now, let's hide our boxes again. Our angle, we want to set this to degrees. Our angle is going to be these mapped dimensions, and our plane will be our centroid points, because we want these to rotate around their individual volumes. So now we can see a couple of things that are happening. I'll turn off the lines. We don't need those. I'll turn off the centroid. Here's our focus point. So what we can see is that our focus point, our boxes are completely kind of open in terms of their orientation through the volume, and then the further away they get, they move to be flat. Well, let's come back to our target values. Actually, we're going to leave it 0 to 90 is nice. Those are the two extremes. But let's come back to our source domain, where we can even create a new panel and we can override some of these values. And so I'm going to set it from, let's say, 0 to, let's say 50. And 0 to 50 will basically be the point, or the object closest to the focus point will stay open. What we should see is more of the boxes rotate to a closed condition, because anything greater than 50 should then be mapped to 90. So basically this space around here is the 50 point, but then they start mapping back again and changing. And so There's probably a few things we could do to play with that, but for now, let's increase that 0 to 90, 0 to 50. So if we wanted to just have one simple rotation all the way through, we could see that that could be 0 to 120. And again, at our focus point, completely open, and then moving to a place where it's completely closed, this being the furthest point away. As we move our point, if we go back to the MD slider, as that point moves, we see the surface opening up, so being the most open here and the most closed over there. Again, this is happening within a flat plane, but we also built in our ability to manipulate this. So if we come to our control points and come to our two curves that we use to make the lofted surface, and we move these out of the plane, we can see that our wall and our surface, because our surface changes, the boxes are continuing to stay mapped to it. So now we have a wall that has shape to it. We have a series of boxes that are mapped to it, and we have a set of rotations through those. So one nice thing now that as you work on this, if you right click the rotate, we can bake this and group these together, and then it's easy enough to move these out of the way. You can change your wall, you can change the way that your elements are mapped, and then you could export another one. So really simple, a relatively simple way. Hopefully this helps you understand. There's a lot in Grasshopper, there's a lot tied to the data structure, and in this instance starting to alternate the contour lines and also beginning to shift the points. It allows us to control that pattern at an early stage. Then it's easy enough to rotate all of the boxes around their own orientation. So let me know if you have any questions about these things. Have fun, and I'm probably going to do a couple more experiments with the remapping of the numbers, because personally I didn't like that once we got beyond the limit that we set, that the boxes continued to rotate beyond that, or from 0 to 90 and then kind of back to 0 again. And so I'll look at greater control in future tutorials of being able to control what we see here, the rotation for these, but we can use any parameter to map any of these types of things. So I hope this helps clarify a couple things for you. I hope this gives you some opportunities to play with this type of geometry of kind of brick wall of a series of elements, and yeah, hope you have fun. I hope this helps. Let me know if there's any questions. If this was helpful, give the video a like and consider subscribing to the channel. Thanks.